think probably look right.
All right, fine. Hey, everyone. How's it going?
Hey, guys.
Welcome to another episode of Eigenbros. This week, I guess maybe Terence wanted to head back into, circle around, back to superconductivity, because our friend, Salvatore Pais, I don't even know how to pronounce his name, he came out with something else. He came out with a paper, an IEEE.
Yeah. Well, I didn't want to really, I was going to plan on doing Salvatore for a while now anyway, but his IEEE paper was on fusion, so that'll be another day. But we went over his paper on piezoelectric superconductor, room temperature superconductor specifically.
This was kind of, like I said, circling back to the UFO video we kind of did like a month ago.
Yeah.
A month and a half ago at this point.
Yeah, we did the inertial mass reduction device on that one.
Right. And so we wanted to kind of explain some of the physics and sort of ideas of superconductivity, of how to kind of piece together some idea of what he's trying to do.
Yeah, so we hope that we gave you guys some kind of, a little bit of understanding of, or at least what we interpreted his patent as trying to do.
Yeah, so that you can have some talking points in your next conversation at the bar or something. Just be like, "Did you guys hear about that new superconductivity patent that came out?"
That's not new.
Well, it's not new, but you can nonetheless you can hopefully walk away with something from this discussion, and we actually go into a lot of our opinion about Salvatore.
Yeah. So we keep it.
We're still a little skeptical.
Yeah, we're not trying to be too. Well, we want to be as accurate as possible, but we give our opinions too based on just what we've seen.
Where we're perceiving the information, how it's being presented and stuff. It's
Indeed.
It leaves you desiring more, at least as a physicist.
Yeah. But anyway,
nonetheless,
yes. So, guys, just make sure, of course, to like, subscribe, comment, share, all that good stuff helps us out. And then also make sure to check out our Twitter at Eigenbros.
Yeah.
Check out the website eigenbros.com. Check us out on Instagram at Eigenbros, and then on TikTok Eigenbros too. And we will see you guys in a bit.
Yep. 3, 2, 1. Bam! We're live.
We are live.
We're live. Welcome to another episode of Eigenbros. Today, in a very sort of scientific episode of Eigenbros, we are talking about superconductivity.
Yes. But this is like a combination of our sciencey episode with the UFO kind of stuff.
And actually we've kind of been how would you say, blacklisted by YouTube's algorithms because now it's against, what did you say? They kind of bury
conspiracy content.
They bury conspiracy content.
I don't know if it's true if we're blacklisted, but I think, we're not blacklisted. That's a little bit of an exaggeration. But I do think we might have been hit by the algorithm because our view count is lower since the update.
We got the mark.
Yeah.
We're on a government watch list now. Thank you.
We got the YouTube Scarlet Letter.
Yeah, we're like the they think we're probably what's that Unabomber guy? Not the Unabomber guy.
Is it Rudolph?
No, what's the guy? Is it Timothy McVeigh, the scientist guy?
I think I got that wrong the last time. Somebody corrected me in the comments. It was another guy.
Yeah, but you guys know what we're talking about.
Yeah, I forget.
That science guy who like made bombs and stuff.
Yeah.
Anyway, we're not like that. We're properly socialized, I think.
Indeed.
Yeah, I hope. Anyway, so superconductivity. It's not really. It's funny because we understand superconductivity, like physicists, to some degree of simplicity, but then it's escaping our understanding when you try to sort of, how would you say, understand a high temperature superconductor.
Yeah, like there's some magical, or maybe not magical, I'll say, but there's a bit of uncertainty in how to actually achieve a high temperature superconductor.
Right.
Yeah.
Right, because there's some
logically
because of in the classical sense of like in the 1800s in the 1920s, I think when this was discovered, it was as simple as physicists measuring resistivity versus temperature, and like through a material, and then seeing that resistivity goes to 0.
Right.
And then it's like, oh, it disappears at a certain
Or resistance goes to 0. I don't know if resistivity does.
Oh, sorry, resistance goes to 0.
It might, though. I'm not sure.
Material. So they see that and they're like, oh, this is a very interesting property. But yeah, they discovered this, and then they see that it's in a lot of different metals and stuff.
Right.
And now, because physicists are people of extremes, they want to find how to do this in a high temperature environment,
right?
Like, at room temperature. How do we get superconductivity there? And that's the $1 million question, folks.
Right. That's a big question in condensed matter physics, which is the field me and Juan are coming from.
Yeah, and we talked about this in previous episodes. The impact that this would have on the economy and everything else, and our way of life. It would change a lot.
Right. So of course this episode is on the guy Salvatore Cezar Pais, who we've done a podcast on previously, but we discussed more on his inertial mass reduction device. Whereas with this one, we're going to be focusing on his actual superconducting, room temperature superconducting device. So of course, the last podcast we mentioned how our eyebrows are raised to the fucking stratosphere because a guy who does all of this just seems highly unbelievable. He's got patents for high temp superconductor. He's got a mini fusion, compact fusion device, which actually, as of this podcast, there's been some updates on that where he actually published a whole paper on IEEE transactions on plasma physics on the compact fusion device. So I'm sure we'll probably do that on a future episode.
Well, he's putting up or shutting up. That's really the thing about all these great claims about making fusion reactors and making superconductors. This is the avenue that most scientists have to take for their ideas to be battled and tested and made legitimate, as we are kind of discussing now, I guess.
Right, and as the adage says, and physicists use this adage all the time: extraordinary claims require extraordinary evidence.
Right.
So, as a physicist, we're not going to really believe much shit unless there's really a clear logical and defining pathway. So, with that said, I'll just initially say right off the bat that I still don't really think I believe Salvatore. I don't think his stuff can really do what it claims. I'm highly skeptical of it, just because we have the greatest minds working on all of these feats, and he claims to have multiple patents within regimes where the top people haven't even cracked these problems to the level that he has, or that he claims. So I'm very suspicious of a guy who's got an aeronautics background in like microgravity or something, who can hit all of these frontiers. Of course, the classic argument with a lot of people will say is he's back engineering some kind of UFO aircraft or something, which, okay, maybe that's true, but still for him to claim the way that these work seems not viable to me, really.
It's kind of dubious.
Yeah, it seems like something you kind of just come up with when you know how the physics works, but you have kind of a naive approach to doing it. And his papers, the way they're written, don't really speak to me as papers that are written by someone who actually understands to a level of depth the physics behind these things. There's a lot of wordiness with a little bit of math, very basic math, and as you get more exposure to actually reading physics papers, there's like a clear way to see it's kind of an intuition of what is a useful paper or not, because of course as physicists, when we're reading papers all the time, we don't want to sit there and look at a bunch of crap that's not going to really pan out right.
Yeah, bad.
So you get pretty good at honing out what's a crap paper by checking the figures, reading the abstract, looking at the mathematics in the paper real quick.
Looking at the references.
Yeah, looking at the references, and then you kind of get a good, and especially if the person's a good writer and they give a nice little description of what it is, then you're like, okay, I kind of understand this. The concept makes sense to me, so this is probably something worth looking into.
Yeah.
With Salvatore's, I didn't really get that impression from his paper.
No, the biggest...
It gave me crank vibes.
Yeah, so we're sort of prefacing what our takes are. And it's... I kind of agree with Terence. Just to kind of recap what we said last, and it was that him citing sources, like his
he cites himself, so he cites his own inventions for some of his other inventions,
right? Which is
already like a
problem.
No.
Yeah, I mean,
like you can, but like for him to be building up all of these things on top of each other is a little bit. I'm highly skeptical.
No, it is. And then the other thing, the other kind of red flag is that he cites some kind of crank, sort of. People,
guys,
right?
yeah. So people who are like panpsychic, these kind of, they explore in these kind of really dubious realms that aren't
esoteric kind of things.
Well, not even esoteric. Esoteric still gives it too much credibility. It's pretty much debunked.
Okay.
It's these physics, in the realm of like EM drives and things. Yeah.
Oh, yeah.
So things that have already been debunked several times that physicists don't take seriously because it would basically upturn all of modern physics.
Yeah.
So it's a lot of there's a lot of things in here that are a little strange, but of course the legitimacy behind Salvatore, why we even are analyzing these things, is because he actually works with the Navy, and he had the head of the CTO, I think, I forget, the CTO of the Navy, I believe, or maybe not the Navy, but of his division in NALCAD, which is a naval air base for research and development. He actually signed off on his inertial mass reduction patent, as we discussed in the last video. So, there was actually a recent update from the drive. I think I have a link on the drive to Juan, if you want to pull that up, about Salvatore. He actually got transferred to a new sector. So he's no longer at NALCAD anymore, and he's now at SSP. And I forget what SSP stands for, but it's another kind of research division of, I think it's still the Navy as well. And the drive was able to get in contact with him and actually get him to answer a few questions. So
SSP stands for Strategic Systems Programs.
Yeah, so it looks like a really crap website.
But it's an official U.S. Navy website.
Yeah, but I'm not surprised that it looks bad,
Yeah.
But, so that's where he's at now.
HTML, it's not even like...
Right. Yeah, this is a joke that many graduate students and physics people will know, is that most physicists and science people have really shitty websites.
Yeah.
Because they made them like in the 90s and then they don't update them. But, so there's a picture on the drive. I'll put his picture on the video or something.
Yeah.
That just got released with his recent paper in IEEE. And the drive kind of talks about how he answered some questions relating to his compact fusion device. And he gave some really just very bare bones, nothing answers. And I even tried to contact Salvatore, and he's just not doing an interview. So that's already another bad sign to me. But anyway, long story short, I think we should dive into the piezoelectric superconductor. Unless you got some comments.
I mean, just kind of want to, again, give some background to Salvatore Pais, right? He received his, if you want to spell this back at home, Salvatore, and then his last name Pais.
Is it Pais,
Pais,
Spanish?
I guess Pais.
For like country or something?
So I don't know where he's from, so I couldn't tell you. But
okay.
He, Salvatore Pais, I guess, received his PhD in mechanical and aerospace engineering from Case Western Reserve University in Ohio.
Yes. So, and he actually had 2 advisors on his research committee. One of the guys being alive and the other one's no longer living. And they both were researchers in microgravity. Right.
So, he was also a NASA graduate research fellow with NASA, the Glenn Lewis Research Center in Cleveland. He also worked with, NALCAD, like Terence was saying, in Maryland. So he's got quite the CV in the sense that he's been working for like DOD, SSP, like Department of the Navy and stuff like that. And
but he's very much like a physicist, aeronautics engineer background.
Right. Yeah. So it's but nonetheless, it's not like a pure physics thing. It's like he comes from an engineering, applied physics background.
Right. So it's expected that he would be able to work with systems with his hands. Yeah. He's not pure theoretical.
Right. And so a lot of these, the thing is, I don't necessarily blame him for not understanding. Maybe say he does just see superconductivity at room temperature, but him not he wouldn't be able to describe it probably because
that's another red flag we'll kind of point up, is because usually condensed matter physicist, experimentalist, or someone who's like that, who's like an engineer type, they won't necessarily come up with a theory behind it.
No.
So for him to, well, I guess in the patents he doesn't really claim too much theory, which is probably another reason why the math and things are weak, but
he would need to have actual theorists, actual condensed matter theorists look at it.
Yeah, and I think he probably wouldn't be able to come up with this stuff without theory either. Because, you know, you can be an experimentalist, but you're kind of directionless without theorists.
Yeah.
A lot of times. Not always, because, like, for instance, the discovery of superconductivity happened before the theory actually happened.
Exactly.
Right? So it goes both ways.
It's a feedback. It's a feedback system.
Yeah. But to come up with 4 different patents where you're basically on the leading edge beyond every theorist, like, I don't think that's ever been done in the history of anything of physics.
Yeah, this would put us in a new realm of a new era, I guess, in condensed matter.
And if this was actually like true, I would expect, of course, these papers are kind of newish because they're like 2019 and whatnot. And there's been a history of like papers sitting and whatnot over time. You know, this is not unusual physics. Like, I think Einstein's papers sat for what was it, around a few months or a year or something?
I think it was like a year.
Yeah. So I mean, these things can happen, right?
Yeah.
But from what I gather, and this paper, Salvatore's papers have been shown to other physicists who are experts, leading experts in that field, and most of them say it sounds like garbage, or it sounds like physics that doesn't have any kind of weight in what they actually understand. And I tend to think I'm on that same page
because
there.
Right now there are a lot of competing theories about superconductivity, and it's not. We've already had to adjust our understanding of superconductivity, I think, twice or 3 times or something.
Oh, was it?
Well, because the classical superconductivity theory, right, where it's like, you know, all the electrons, like, they just kind of move in a coherent state and stuff, and then they move all together in unison, and so they don't generate any sort of friction, the field of resistance, I guess. So they move it as a band, and yeah, so. But then, like, applying that theory linearly to other materials, it didn't necessarily work out. So a lot of
the logical pathway was not as clean as they were expecting.
So then you had to introduce BCS theory, and I think you have something up here about BCS theory, correct?
Yeah, I do.
Yeah.
I've got some things on that. If you want to go into it.
Yeah. I think it's a perfect segue for that.
Okay.
Because, like we're saying, Salvatore Pais' invention would require a new theory.
Well, there's
or a modification at least.
Well, let me jump in here real quick.
Sure.
So most physicists will know of the BCS theory. This is kind of the classic theory for superconductors.
The working theory today.
Right. And the first superconductors were type 1, which is like metal superconductors that undergo BCS theory or you know, the generation of Cooper pairs, which is how you get the zero resistance, because they have some kind of coupling with the lattice. So, like, electrons will move within a lattice, and then they have this coupled system with the lattice and the electron, or the charge carrier. But there is another type of superconductivity that I just learned researching this, which I had never heard of, which is called bipolaron or something. So there are these quasi-particles called polarons.
Polarons.
So you're familiar with one. So maybe
I've read a couple. No, I've read about it a couple times.
Okay, so I didn't really go into depth on it, but I do know that there are other theories besides BCS explanations. And I think, I'm not sure if Salvatore's would fall under this, but I know his superconductor is kind of weird because it's using like currents and AC currents with a resonant frequency, rather than, like, you know, taking something down to a certain temperature and then, you know, cooling the atoms like that. He's like controlling the lattice somehow.
Interesting. Well, what we also mean by lattice, for some of you folks out here, it's we're talking about the crystal that you're working with or whatever that you're measuring.
And crystal doesn't have to mean like a diamond or anything.
Yeah.
Anything that has like kind of any
material that
an organized structure is a crystal, we call.
Right. Anything that has atoms that are arranged in a way that it's sort of symmetrical or has some kind of
has some symmetry
logics,
properties to it.
It would be considered a crystal. And then that crystal is composed of lattices and whatever. So just you can think about it synonymously, I guess, for now. But I know, technically speaking, they're not the same. But nonetheless, you can operate in that framework. So there are a lot of competing theories, and I think the type of superconductor that I used to work with iron selenide, and that was a 2D material kind of compound, and we're actually looking. I mean, we've abandoned the project, so it's kind of like I can talk about it freely. But
okay.
At the time, we were trying to see if what would happen when you take a superconductor like iron selenide, and you bring it down to a few nanometers. So to
what
where
do you mean, nanotemps?
No, nanometers. Like you bring the thickness down of the I guess the material to orders of magnitude that would put it within the range of the coherence length of the actual Cooper pairs. So it's a very interesting question, because then it's like, okay, what happens to the wave function of the electrons pairing together, and like, well, what happens? Like that's a fundamental question.
So you're studying like the real physics behind that.
Yeah.
Okay.
It was a real fundamental, cool question, but I'm not going to get into it. But basically, we had to abandon the project, and so, fundamentally, there's still a lot that we have yet to understand about superconductivity, and
quite a lot. And the leading people right now are, I mean, the experts in this field. They're so
grasping.
They're still. I mean, the experts in this field, their closest room temperature superconductors are nothing like the one in Salvatore's patent.
We're talking about putting the superconductors in like extreme, how would you say,
pressures?
Yeah, extreme pressures.
Yeah,
specifically.
We're actually. So I actually have a chart that I found, and it's actually on that notes. So it's in the chemistry.
This one.
Scroll. Yeah, there you go. So if you look at that one, there's a graph, and I have this on my Twitter as well. If you guys want to take a look at my Twitter, but it's a
iron selenide is right here.
yeah, it's a chart basically showing temperature versus the year of discovery, and we're actually really close to room temperature superconductors. But the hack behind that is they use these gigapascal pressures to achieve this. So normal atmospheric temperature is like 101 kilopascals or something, which is 10 to the 3 or 1,000 pascals.
Yeah.
So this one's in the billions of pascals of pressure. So it's not really practical yet, but we're just trying to get to that level of room temperature first. And they think they know which one it's going to be. So they're trying to develop yttrium, I think. A yttrium superhydride. Yeah, it's like a YH10 or something. And that one is supposed to reach the first room temperature capability, and it should be like around 53 degrees Celsius or something.
Yeah.
But right now, I think we've got one pretty close. The highest room temperature, or the highest temperature superconductor right now is like lanthanum. Can you look at it once? Like lanthanum hydride or something?
Yeah, lanthanum hydride 10.
Yeah, so LaH10. And that one's at like
10, but at 180 gigapascals.
Yeah.
And it's I would say it's below 300K.
Yeah, but it's like 270 or something, right?
Yeah, it looks like that.
Yeah, so it's getting close.
Right.
But these are the leading people in the field right now. So they're all working with superhydrides, which has nothing to do with what Salvatore's patent is.
And then also you're building like these, and actually in my group, we work with superconductivity.
Yeah.
So we work with pressure cells like that, and we have to make, like for instance, a postdoc in my group, she's working on hafnium sulfide, so H2S. And that's not even close. It's probably 200 Kelvin, maybe, and at 155 gigapascals. And they have to build like this pressure cell thing that to create an immense amount of
pressures for,
and just to achieve that close enough. And
right.
I mean, here's the thing, though. You look at certain compounds, like like iron selenide looks like it's about maybe one. How would I say about 100K, I think. Yeah. And it's but it's not as, how would you say, the lattice structure is different than something like a yttrium hydride
or superhydride.
Yeah, or a lanthanum hydride, where it's like the lattice structure is like huge because you got a bunch of atoms and stuff.
Yeah.
So that's kind of like, it's kind of a big question for a lot of physicists because there's not a clear, like, how would I say?
It doesn't follow logically.
It doesn't follow logically, exactly.
But the whole thing with the superhydrides is, this is the big discovery within these last couple of years, is people figured out that when you start loading up hydrogen on a metal, then you actually get the ability to reach these room temp superconducting levels right now. So people are all scrambling to make the yttrium hydride or the yttrium hydrogen 10 right now, because those superhydrides are kind of the way in leading edge research for superconducting.
And try to understand why it is that hydrogen allows them to.
Right.
That, yeah.
So they're trying to push that limit right now. So that's pretty much where the leading people are on, which is very different from Salvatore's. I keep saying that, of course, and I'll get to how it's different eventually. But there's many, many different types of superconductors.
Yeah.
And the chart that I have here even shows like the different types. So yeah, that's what Juan was basically saying, is the pathways are not logical. It just depends on what you're analyzing, the material you're analyzing.
Yeah.
And we're still trying to actually we're trying to figure out the theory behind this stuff.
Exactly.
And like what links them all, I guess.
Right. You get into something very exotic and kind of new, sort of topological. I think there are some people that want to involve sort of topological properties of the compounds that allow them to do all this stuff. And I think you brought up something about vile semimetals, right?
I did. Let's not jump to that just yet. But it's related to Salvatore's his version of the superconductor.
Yeah, because I work very closely with all this kind of theory stuff. And
okay. But you wanted to do BCS theory. Let's take a step back and actually talk a little about BCS.
Oh, yeah.
So that video actually is on BCS. We can include it in the podcast. It's a nice little demonstration.
Okay.
So
yeah, this will be a good segue then.
Sure.
We'll play it for you folks at home. Just in case you wanted a quick little, how would you say?
Crash course
in it. And hopefully it's pretty sufficient. So, yeah. So also, before I start, there's a picture of red dots arranged in a pattern. Well, just like a grid sort of thing. Just so you can imagine this while it's playing.
Yeah, so for the audio listeners, we're just showing like a little visual representation of what happens with what BCS theory describes.
Whoops, here we go.
Lattice. Now, of course, they are not stationary. They are actually moving. So in order for us to understand why a lattice causes electrons to slow down, I want you to imagine a room full of punching bags like so. And you would appreciate the fact that this would be fairly easy to run through because the punching bags are arranged geometrically. However, what would happen if all of these punching bags were to be moving quite randomly? Well, of course, you would run into them regularly. And that would cause two things to happen. You would slow down, and your progress to the other side of the room would certainly be decreased. Secondly, you would cause a number of other punching bags to vibrate even more violently as you collide with them. So here I have my electron passing through the lattice. As you can see, two things happen. Number one, the electron gets slowed down as it collides with the vibrating lattice. That, in essence, will cause the electrons to slow down, so conductivity decreases. Secondly, the electrons will transfer some of that energy to the lattice, which will vibrate more violently and therefore causing it to heat up further. So that gives us the setup as to how the BCS theory came about. Before I go on and explaining the BCS theory, I want you to understand that the theory describes what we refer to as type 1 superconductors. And type 1 superconductors are materials that are metals or metalloids that already have some conductivity at room temperature. And so they display superconductivity at really low temperatures. But like I said, we are only interested in metals and metalloids. And this periodic table here gives you the critical temperatures of a variety of different substances.
And for type 1 superconductors, it's pretty logical, right? Why they would become superconducting.
Yeah.
Because once you get to cold enough temperatures where the atoms, the vibrations of the lattice start minimizing, the electrons are more free to move
Exactly.
Yeah. So,
and you can, if you want to jump in this video,
Sure.
jump to like 6 minutes or something. There's another good part. Keep going. Maybe low, maybe even more. It gets back to it. Yeah.
This
And
one?
then he kind of shows what happens to the lattice when a electron enters in the
in the state.
yeah.
Okay. Here we go.
once they get below the critical temperature. But for the sake of this demonstration, I'm going to have them static. But please understand that they will be vibrating slightly. To help us to appreciate it better, I'm going to introduce the bonds in between the atoms so that we can more easily see the effect of electrons on this crystalline lattice. And what would happen is if I were to place an electron in this particular area. Now this is, of course, occurs at below the critical temperature. And what happens is that the atoms surrounding this electron are attracted to this because of the fact that this is negatively charged and these are positively charged. So what we're getting here is a distortion of the lattice. Well, that means we get an increased positiveness here in this distortion. And this is called a phonon, this particular distortion. And so what we have here is a phonon-electron interaction. But the important thing is that the electron here will cause this distortion. If I move this electron, of course, over here, then the distortion would actually occur over there, and these would return back to normal. So the presence of the electron as it moves the lattice causes the lattice to distort around it. But what does this distortion also do? Well, another electron is a
So, I mean, he's kind of going really slow, but
He is.
yeah, he's spending too much time just, what if we place this guy over here? I mean, he wants to reiterate that.
But I guess we can kind of leave it on that note.
Well, I mean, he shows the interaction between the electrons and electrons.
Right, but we can talk about that.
Okay.
So basically, after that distortion, you get a kind of higher density of protons at that certain area, right, where that electron sits.
Yeah.
So then other electrons become attracted to that area, and then if you get another attracted electron to that area, the two electrons are now bound as a kind of coupled system. So they have a Cooper pair. They become Cooper pairs. And then this continues on for all the electrons in the system. And then now they kind of flow freely through this lattice because now they have this distortion carrying them through too, to where it's giving them zero resistance essentially.
Yeah. They're all paired up and doing a dance, basically.
Yeah.
And it's a very interesting theory, and you can look into it on Wikipedia. There's a lot of sources because it's a pretty well thought out theory at this point.
Right.
And I think
They have some good explanations like this, very simple.
Yeah, and but nonetheless, that's kind of the crash course to BCS theory. But as far as how it relates to our friend Salvatore Pais or whatever.
I don't know what to say. I say Pais.
Pais, yeah. Call him Salvi. Yeah. He's coming at us with a whole different kind of how would you say, just a whole different approach.
Yeah.
Like we okay, looking at the patent, right? So going back to that, the patent on Google, if you Google this, it's simply, you can just Google.
I'll put it on the video too.
For the audio listeners, it's a piezoelectricity-induced room temperature superconductor. And, of course, you just look up his name, Pais, his last name, you should be able to find it. But there are claims that are being made. And what is claimed is a room temperature superconductor comprising of a wire, an insulator core, and a metal coating. The metal coating is deposited around the insulating core, and the metal coating deposited on the core. Wait, what? Yeah, and then when pulsed current is passed through, so when an AC current, like Terence is saying, is passed through the wire, then while the wire is, I guess, vibrating, the room temperature superconductivity is induced.
If you look at that notes too, Juan, I have some Control F parts for that patent. I forget what they are, so maybe you should take a look.
Okay. But I guess you can talk about the diagram here, I guess, in the meantime. But
yeah, so basically it's just like this, it's this weird like insulator with a metal on the outside, and then it also has a piezoelectric ceramic on the outside. And then what happens is apparently that piezoelectric, or I guess I should explain what piezoelectric means. So piezoelectric things can be, imagine if you have some kind of lattice, piezoelectric materials can be stimulated by electricity or vice versa. So if you move a material's lattice, then it might induce electric currents. So piezoelectric materials just have some kind of relationship between the lattice and then electricity. So it either generates electricity or the electricity moves the lattice. So with Salvatore's invention here, he has some piezoelectric material that stimulates the metal, which is surrounded by some insulating material.
Yeah. So the technical definition of something that's piezoelectric is, or the property of piezoelectricity is the electric charge is when an electric charge accumulates in certain materials, right? So in response to applied mechanical stress. So so that's kind of
right. So you're moving the materials lattice somehow,
you're
and then that's
interacting,
inducing some kind of electrical current.
Yes, you're stressing, or you're kind of sort of causing lattice distortions in a way where you sort of you accumulate charges in certain regions and stuff.
Yes, and the process can be reversed too. Yeah. So you can stimulate it electronically, and then that moves the lattice as well.
Right. So in a sense,
so I think what Salvatore's is the inverse, where you're using electricity to stimulate the lattice.
Right. So the three parameters here that Terence was sort of bringing up was they include temperature, current density, and applied magnetic field. So these parameters have one thing in common according to the patent, and that's the basically cohesive motion of the charges of the electrons, the charge carriers. He says control of this motion via basically tuning the frequency or spin of charged matter subjected to acceleration by, I guess, the field. The writing is kind of bad. I'm transcribing live because some of the language is weird. So it may lead to the achievement of room temperature superconductivity, especially if the charged matter is inhomogeneous. Now, I can sort of see how this can align with BCS in a way that would make sense.
Yeah.
Where, if you're causing lattice distortions because of a piezoelectric
induction,
then I can sort of maybe argue that. But
that's the same kind of thought I had.
Yeah.
I was like, this actually, at least with this patent that I've read, it actually, I can come up with something that kind of sounds physically possible to me.
Yeah.
Because basically what it sounds like he's doing is he's making it so that instead of the electrons are bending the lattice, he's making it somehow so that the lattice bends to accommodate the electrons somehow.
Yeah.
So the electrons are not the cause of the lattice coupling, I guess. And he's saying that the pulsed current that he sends with that into that piezoelectric material is somehow inducing that lattice to move those electrons, which sounds very feasible, right?
Sure.
But the only thing is, I don't think this is something that's going to make sense because, for one, I feel like someone would have already done this. I've seen, and I have some papers already that are talking about piezoelectricity and superconducting, and they're still kind of working it out. So I think, and with the mathematics that I saw in those papers, it didn't seem like something that was really simple. And then two,
well, physicists wouldn't do this because I would tell you right now, physicists we play with toy models. We wouldn't want to complicate it with whatever he's doing. He's like,
I could see a physicist doing this if they knew that it could achieve a superconducting state.
Yes.
Yeah.
But we kind of go for the simplest kind of experiment possible.
That's true.
We wouldn't necessarily go through all this stuff of wrapping a wire around this
Well, let's look at the
material.
simpler one without the wire.
Okay.
So the figure 1 has the simplest system, but that's really a simple system, man. Because I mean, think about what we've done in labs. Like I've done projects where I would do nanowires and make devices. So we're in condensed matter, we're like on that edge of engineering, and we would definitely see a project like this on piezoelectric induced superconductors if it was something someone thought of. The only thing is, I don't see how he would be able to. So what I'm assuming is his pulsed current is somehow sending like a phonon wave or something to move those electrons. But then I'm thinking like that's not going to be BCS theory. So you need that kind of attraction with these electrons somehow. And I don't know how you would control that with a pulsed current. It doesn't make sense to me.
Well, the argument, I guess, I don't know. Okay, well, let me just, maybe we should kind of describe what he's saying, because he's saying at present time it's believed that the mechanism of superconductivity can be induced by bipolarons or Cooper pairs, and like he's saying, but like you were saying earlier, bipolarons are quasi-particles of two polarons. So a polaron is...
Oh, so he is claiming the polaron stuff.
Well, he's just saying, like, right now, as we understand, superconductivity is...
Oh, he's just describing either BCS or
Right.
polaron.
So, he's just saying a quasi-particle is used in our understanding of physics to try to make sense of how the electrons interact and the atoms in the material. So
right, and to quickly just add, a phonon would be an example of a quasi-particle. Right. So, like, a phonon is just the quantum of sound. So, you know, a quasi-particle is just a way of saying, like, it's not actually a particle, but we can describe some kind of vibration or something, like, as Juan just said,
its effects
as a particle. Yeah. So we can pretend it's a particle, and the math works out nice.
Right. And then he just kind of goes into BCS theory. And he just says this: an arbitrary small attraction between electrons in a metal can cause a paired state, Cooper pairs, to have a lower energy than the Fermi energy, which implies that the pair is bound. So in conventional BCS superconductors, this attraction is due to electron-phonon interactions, which is what the video was saying. And he says the important realization is that independent of physical mechanisms, the key to observe superconductivity is the electron lattice coupling.
Yes.
So strong electron lattice interactions can drive or accelerate the... Oh, he says the lattice and electron interactions are sort of how would he's manipulating it.
They're coupled.
Yeah, but he's manipulating it through, like, alternating, I guess, the frequency in the wire or whatever.
Yes, he's using the piezoelectric effect to alter the lattice structure to influence those photon interactions, I guess. But I think he specifically had it at the resonant frequency is when it's the strongest point, which makes sense usually, right? Most things when they're hit at their resonant frequency is going to be their strongest point. But yeah, I mean, it sounds like it. Like logically, that makes
it's like
it sounds like it could make sense.
We were saying.
Yeah,
we were saying like he's just trying to achieve lattice distortion to drive the Cooper pair interaction, and then So he's just doing a little bit of engineering, I guess. Now, the validity of this would be that, well, the interesting part of it would be knowing what material he's using, but I don't think it's. He doesn't. He says aluminum for the metal, and then for the piezoelectric ceramic, he says some kind of like titanate. I have it in the notes. So this should be reproducible, though.
It should be. It should be. From the way he describes it, I mean, I already have an idea of how I could build something like that. So I imagine somebody could try that. But yeah, it seems naively simple to me, though. From the papers that I've researched on the piezoelectric effect and superconductivity that say something like similar to this, they seem much more complex. And I feel like someone would have already done something like this if it was that simple. I found 2 papers that were related to piezoelectric effect and superconductivity, and I have them in the notes.
Published before him or published after?
They are published, I think both are before him.
Okay, interesting.
So that's another thing I thought maybe he just took that idea and then ran with it.
That happens in science, where like if people sleep on certain papers, somebody can come out with something else.
Yeah, but their papers were much more complex. So it seems like something that people have already thought of, and then they're trying to make it work. You know, but they realize that there's some kind of deeper interactions or something going on, or just more. It's more complex of an image than they expected. So, I'm not convinced because it seems like it's not that simple.
I guess we'll see. I mean, we'll have to see what papers come out and see.
We'll take a look at the papers I have here.
Okay.
So I actually have them on the notes.
Yeah. So you have. So there's one here: superconductivity from piezoelectric interactions in vial semimetals.
Yes.
And this was published last summer. But it's in the archives. So by the way, archives are archives.
Well, I already checked to see it's an AIP too.
Oh, okay. So for the folks at home, this is just
this is the crank
archive
potential.
Archive is not.
It's easier to get a crank paper in there. Is what I mean.
Sure. The archives are just basically a place where most scientists go to let other scientists know that what they're working on.
They want to allow you to access the paper because a lot of times when you look for research papers, they're behind a paywall because most of these journals charge an arm and a leg. But they know that most of these people work with universities, so they just pay for the subscriptions. But I usually get the archive links if I can, or I'll just go to Sci-Hub or something, and then I'll get my paper that way. So this one's from the archive, so it's openly available. But it was published in AIP or something, I think. I think I found that originally. So it's in a credible journal.
Right.
But you see, if you're looking at it one already, you see it's got quantum field theory involved. And
it's got some Green's function stuff.
Of course, the vial fermions, which are kind of complicated.
Propagators and stuff. It's talking about nodal lines. It's all fine and dandy. It's just I mean, this is way more physics than he probably ever will write down, just because his background is not pure physics.
Yeah,
but
and he's doing a patent too, which is not a research paper.
And this is clearly more
for the physics,
more physical. More the physicists wrote this paper.
I get what you're saying. So maybe the complication lies within the physics and not the actual.
Because he might just be an engineering thing where he just put it all together and then he's like, I don't know. I mean, maybe this works out this way.
Right.
Yeah,
and you can see that with other patents too, right? Because they're kind of they can be bare bones, kind of sparse. It's only when you see the white papers when they can get more in depth.
I guarantee you, if this works, physicists will be clamoring to try to describe why it works.
Yeah.
If it works. Now, that's kind of the thing, I think.
But take a look at that other paper, too. I have another one on there that has something similar. Maybe
should we say a little bit about what the paper says?
Okay. If you want to read the abstract, that's the best option.
So we present an analytical low-energy theory of piezoelectric electron-phonon interactions in undoped vial semimetals. Vial, by the way, is spelled W-E-Y-L. Taking into account Coulomb interactions. So we show that piezoelectric interactions generate long-range attractive potential between vial fermions. This potential comes with the characteristic angular anisotropy. From the one loop, it gets into
quantum field theory.
Some quantum theory for many particle systems, but it's so nonetheless. Oh, what? Oh, they consider tantalum arsenide. We have worked with tantalum arsenide in my group. Interesting. Okay. They say here, for insulators or semiconductors, the most important couplings between electrons and acoustic phonons generally originate from either deformation potential or the piezoelectric interaction. Right.
So this is where I was like, okay, this has some alignment with Salvatore's paper.
Right. And that's cited. There's two more papers that they pull this from too. So this is apparently a well documented.
It's something that people are looking into.
Yeah.
But they specifically say I think the charge carriers in this case are Vial fermions,
which are a specific. It's just a category for certain types of electrons. Vial materials, or I guess vial semimetal. I guess maybe we can kind of.
I have that.
Yeah, you do.
Yeah.
They say, well.
It's kind of still high level.
How can I put it? But in simple terms, it's mainly. How would I say this without getting into all the terminology? Because there's so much terminology that we would need to build on. I would just say, let's just say that there are certain types that not all electrons are created equal. Some of them are different depending on the material, but this material is categorically a vile material.
I don't know if that's a great explanation, because all electrons should be the same, right? What's the difference between
it depends on the band structure of the material, and so if you can imagine, this is getting a little technical.
So it's probably like an effective electron then.
So I can sort of give you a little rundown. So like for some vile metals, I guess, or some vile materials, what you'll have is like the band structure. Sometimes one band will kiss the conduction band, and it'll form like basically a way for the carriers to pretty much go straight through to the so the electrons to become. So it's pretty easy for them to just become conducting.
Okay.
So in a sense, they have special properties. If there's a material where a lot of the bands are touching, then that means like there are multiple points where the electrons can they become conducting. You know what I'm saying?
No, because I didn't really understand vile, because it said they had to do with chirality in the wiki.
Yeah. Chirality is just how they behave inside of the material, so they can sort of interact in such a way where they obtain angular momentum and stuff, and they start behaving non-trivial.
But what's the angular momentum? Is it an orbital angular momentum?
Yeah, I believe so.
Okay. So yeah, it's a little bit more complex. That's what I was saying, though. I think this is more complicated. The whole point of me getting that paper was to say that it seems like the interactions are more complex than what Salvatore is going with.
I don't think I don't know if that's what you look for in a patent, but what I'm saying is, I don't necessarily blame him, because I know he's not a physicist, so
it's a weak I guess argument against his patent, because it's like, he's not going to go into the physics, but I'm just not sure if it's going to be something as simple as a wire with aluminum piezoelectric material and then any insulator. It sounds too good to be true, almost.
Yeah.
Very simple setup.
Yeah, and I think you highlighted this in the patent. You said consider an experimental setup at standard room temperature and pressure, right? Okay, yeah. Did you want to talk about that? Because I guess that's the...
I guess, if I put it on the paper. I can't remember.
Because, okay, so what Salvatore Pais' patent says is you have a setup where there's standard room temperature and pressure. We're talking about 300 Kelvin, pressure 1 atmosphere, right? Okay. Where current carrying aluminum coated wire is vibrated in a sort of, he's saying, abrupt accelerated manner by being struck with a non-conductive element such as a Teflon pick in order to generate accelerated vibrations. So he's literally saying you pluck it like a guitar string.
I think he even says that exact quote in his...
Oh, does he? Okay. Yeah. Well, more effective means by vibrating a wire in tension is by use of electromagnetic plucking coil. The coil is rapidly energized and de-energized using a DC or AC current, and the induced flux couples with the wire, and you can pretty much also create an alternating vibration inside the wire. So he talks about how you can alternately coat the wire, dope with submicron sized ferrite particles, blah, blah, blah.
That's probably good enough.
Yeah. So that's the idea. But he says this method of vibration would be greatly conducive to superconductivity, since enablement of the Meissner effect would be possible.
I don't know how that claim is going to be true. And the Meissner effect, I feel like, only shows up in type 1 superconductors, no?
Yeah.
Because Meissner effect has to do with repulsion of any external field.
Yeah, so. The pairs, it's because the pairs, when the electrons pair up, they form their own kind of, how would you say, they don't want to lose the wave function doesn't want to be disturbed. So it's like almost pushing back at the external field because it's trying to maintain its state.
That's probably something you had to learn in your many particle class. Okay, because I'm not.
This was
it's in the
outside.
weeds for me, so I don't really know. All I know is the basic properties from electromagnetism is that any kind of superconducting metal is going to repel an external field completely.
Yeah. No, it's going to want to, just because of the nature of the wave functions, how it tries to minimize, how it doesn't want to die. So it's like, Anyway, you can think about it that way. But
the particles don't have feelings, guys.
They don't have feelings, but they don't want to die. You know, they want to be paired up forever. So
it means it's more energy. It's more energetically favorable or something for them
to be paired up. Yeah, exactly. So, what else did we want to go into? Because it seems kind of. I know we're running low on time here. I don't know if we didn't. I probably didn't even touch on everything, did we?
But I think we gave a good enough kind of simple explanation of what his patent is, because I don't want to get so heavy in it, because the patent is already so wordy and just, it's a lot of words. I just want to make it simple enough where someone who doesn't know physics or knows a little bit can understand kind of what this is supposed to be.
Yeah.
And just, I guess, what general thoughts you have on it. Do you have any thoughts about this patent? What do you think? Does it seem legit? Does it seem like something that could happen?
I mean, if he did stumble upon this, then it's just a matter of testing it. I can't say.
Yeah, and this seems like something that's very
testable, 100%.
So
it's very easy to even do. I could probably go do it in my lab now.
Right. I don't see. Yeah. If this is that simple, I can't believe it would be that simple, though. It just seems so easy that I feel like someone would have had to do this, because people work with piezoelectric materials all the time.
Yeah.
So I'm not convinced. Of course, I'm really unconvinced because of just his whole history.
Yeah.
He has so many patents claiming to do these revolutionary technologies. Just doesn't seem likely. And this one seems so simple. It doesn't seem probable to me, because, I mean, think about the materials. It's a wire that's a metal, that's aluminum. We have aluminum everywhere. It's not a kind of weird metal that we're trying to synthesize. The piezoelectric material, you can find that anywhere. It's like, if you look, can you look at the notes one? I think it should say like PZT. The piezo ceramic is something you can easily find.
PZT coating.
What's the material?
It just says 120. I don't know.
Oh, that's from the patent. What is on the patent? But go to the website and see the material. It should be like lanthanum. Well, whatever it is.
No, it's not in there. It's not in here. Sorry.
Okay, so it's like lanthanum titanate something. Very easy to get. And then they have the insulator, which he says you can use just any insulating material.
Yeah.
And that's literally all there is to the setup. And then apparently there's Cooper pairs that can form between the boundary of the insulator and the metal. So I guess he says it's a little bit different from a normal superconductor in that respect, because it's like the superconducting mode is on the boundary between two materials. But honestly, it seems so simple. I would be shocked if it worked. I would be shocked if it worked, especially with the level that, people are going to try things like that are that simple, who work in that area, because, if you're in the leading edge of piezoelectrics and superconducting, that seems like it would be such a logical thing to do if all of those materials were involved that are so easy to get.
Yeah. But sometimes it takes one guy to see a vantage point, to be like, well, there's a couple theory papers that are saying that you can do this by inducing, you can distort the lattice in this way. And maybe he's like, well, we can do this. And, you play around with a couple things and then you end up at this. So I'm saying it could very well be possible. The only thing is, my only condition is that there's a couple fishy things about him that just seem...
His background is very fishy.
His background is, yeah.
And also the paper is written in a fishy way, too. Because even like the descriptions of things are not very good.
Yeah.
And also... like you would expect him to say more kind of about the material properties and things.
Yeah, characterizing this material.
Yeah, maybe. And usually when you read papers like this that are really hard to understand, they're probably wrong or fake. Because usually something this simple, I feel like, would be very understandable to someone, especially us who are condensed matter physicists. it seems unlikely that I would not be able to grasp that. Because if it's still operating on the same BCS theory, I don't see why it has to be such a complex written paper. I feel like there would be a very easy explanation to this.
Yeah.
Yeah. So these are all like kind of, they're not great arguments, but at least it shows you what a physicist would think when they see this.
Right. And look, this is not some brainwashing stuff. This is just literally.
Yeah, exactly. We have no vested interest to give a fuck or not. Actually, honestly, I would rather have this be real, because then if this is real shit, then I get to see,
amazing technology.
So yeah, I don't care either way. But from what I've seen, this, I'm not convinced. At the end of the day, I'm not really convinced.
It needs to be tested extensively, and we need to get more data. We need to get something. We need to get people to do this and then see what we get. And understanding it, obviously, and understanding the mechanism is another thing. I don't put it past an engineer just making something because they wanted to, and then they're just playing around.
Right, right. They usually are going to be looking up some theory. For something like this, it would make sense to have a theoretical backbone to
or
it.
At least a theoretical intuition or something. Yeah.
Because the advent of superconductivity made sense to come experimentally, right?
Yeah.
Logically, because he could just be doing he's just testing the material properties of a material when you go down lower and lower in temperature.
Yeah.
With this kind of setup, it's more of like, I guess if you understand BCS theory, you can maybe see, what does a piezoelectricity do because of lattice vibrations, but it's still not so clear. You would probably need some kind of theoretical backbone to even want to do this.
That's what I'm saying. Unless he read these papers from previously published, which is possible.
Right, right.
But it doesn't even seem to be in his forte
at
all, because he works with, what did you say? He works with microgravity
and stuff like that. Yeah.
Which it seems to be that he's proving something. He's working backwards because he wants to. He was trying to build a microgravity system, or
he's trying to build a hybrid spacecraft that goes air to sea. And a lot of the inventions that he has with these patents are necessary to make that thing work.
And then they're insane. They involve an insane amount of physics.
They're like next level beyond what we know physics.
Yeah.
And it's not typical for it. It's unprecedented actually for someone to be able to do that.
And the fact that he still has a job at the naval labs, I don't know if that's. I'm curious,
but I don't know, man. The thing is, like, smart people are not immune to quackery, right? So
no.
And the guy who's a CTO that corroborated him has no background in any of this either. So, I mean, you never know. There's crazy people even who are smart. So I just don't know, man. I'm not going to say for sure. There could also be another side of this story that's more like political or bureaucratic that we don't know. So maybe there's something that's just higher level that we just don't get, like this is for disinformation or something. Like, I don't know. Who knows?
Yeah.
The military has all kinds of ways. I don't understand that. I don't understand that part of life. I don't get military stuff like that. So
same.
Who knows,
Yeah.
But the physics, it sits more in the realm of, I feel, bullshittery.
Your bullshit meters.
Yeah, bullshittery is kind of the realm I'm in. It's very light, though. I think I'm only about
80-20?
Well,
70-30? 60?
So I think probably I'm on the lines of like more like 65% I believe it's bullshit.
I see.
Yeah. So it's more than 50%, but I'm not going to say it's fully bullshit until I really can prove it.
Yeah.
So I'm sure we'll have more on this too, especially now that Salvatore has released his IEEE paper, and that's more of like actually
legit
paper. Like, it's a written paper. Although I looked at it and it's bad. I'll just give you a kind of a sneak peek. It's not looking good.
Oh, God.
The math looks very basic and not like something you would see in a typical paper.
Yikes. That's why it's an IEEE and not in a physics journal.
Yeah, but I have to look at other IEEE papers to see how in depth they go. But like, it looks like it doesn't look like any kind of paper I've read that would be on something like this.
No, that's what I'm saying. You would need a theoretical physicist. And
it was not theoretical. It's just a lot of words and very little math.
Yikes.
Which doesn't seem to make sense to me.
Yeah, it's not good.
Yeah,
All right.
but who
well,
knows?
Then he might not know what he's doing, but
Yeah.
still.
And it's also got they also think about Salvatore is he also has this crank way too of I've noticed a lot of cranks. They always like to talk about how things are going to be revolutionary and how you should trust in their ability.
Really?
Because of like
trust. He said trust.
Not trust, but he has that vibe of like things are possible. Look at my credentials and realize that these things are possible. It's a very like trust-oriented framework, which is the crank's bread and butter, right? Everything's trust me. I have the info. You don't have the info.
I have the documents.
But it's very easy to like just give the evidence. Where our physicists are all about evidence-based. So we want to know simplified, easy, real testable things. Mm-hmm. We're not trust-based, which makes me a little bit worried too in that sense.
I would be too. I have trust issues too, Terrence. And with that, I think we'll be signing off. I guess stick around for the outro.
Yep.
Yeah. Thank you.
Thank you
for making it this far once again. We didn't really have a question, did we? I mean, there's really no. Well, I mean,
we can ask people what they thought.
Yeah, you can maybe. Hey, tell us what you thought.
Salvatore bullshit or not? Leave us in the comments.
Think he's a bullshitter? Maybe not. We'll see. Make sure to like our video, like our other videos. Go back in the history, scroll, kind of go through, like everything, comment something on it, share it. Most importantly, share it. Share it with some of your science buddies or your science friends, science gals, you name it. Just, spread the word.
Indeed. And also subscribe.
And subscribe. Yeah.
So just make sure you guys check out our website, Eigenbros.com. Check us out at Eigenbros on Twitter. And then check us out at Eigenbros on Instagram. And then Eigenbros 2 on TikTok. And we will see you guys next video.
Yes.